Okay, we're going to start looking at the example problems that would normally occur on Thursday. This is the first example problem. It is a wooden laminated box. It would be a beam, so it's hollow. There's four sections. There's like a top, a bottom, and two sides. We want to determine the maximum shear stress in the box beam if the maximum shear is 250 pounds. I've done some preliminary drawings here just to kind of like make it easier. This little blue drawing with the dimensions would be if I cut the box in half, right at where we're looking at. So if I cut it right here, I just turn it completely sideways, then I would have this little blue box. Because remember, that's what we're really interested in, is half of this, especially to get Q. So I thought I'd make it easier to visualize by cutting it right here. And I got the 4-inch dimension from just the web, just this little piece from here to here, is 8 inches. So half of that is 4 inches. But notice it's not all the way to the top. It's just to where they intersect right here. The top has a thickness of 1 inch right here, which I didn't draw because I figured those lines would be too close. But the top part is 8 inches, and I got that from 6 inches plus 1 plus 1. So I just turned it to the side. We'll use that in a second, and it will make more sense when we calculate Q. First, let's get I. Now I'm going to get I first because I want to make it clear, that you need to get I for the whole shape. I is for the whole shape. The Q stuff is for the half shape, which we'll get to. So right now let's just get I for the entire shape. And this one's nice. The centroid for both of these, for a big box minus a small box, the big outer box minus a smaller inner box, you don't need the parallel axis theorem because the centroid for both of those guys is in the middle. So we just need to do base height cubed minus base height cubed to get the moment of inertia of the entire thing. So I'm going to do the big outer box. The base is 8 inches. So 1 plus 6 plus 1. The height is 10 inches. 8 plus 1 plus 1. So 10 inches. Oops, that's a number sign. So that's cubed. And that's divided by 12. I'm going to subtract that from the inner box. This little inner box right here where there's nothing. And the base for that is just the 6 inches. This right here, 6 inches. So 6 inches times its height is 8 inches. You can see that from the interface to that interface is 8 inches. That is cubed. And that little set needs to be divided by 12. And I do that, and I'll get 410.67 inches to the third for my I. Again, I'll reiterate that the moment of inertia for all these problems to get into the BQIT equation is the entire moment of inertia, not the half part. The half part is for Q, which we'll do now. So we need to get Q, then remember that's AP times Y bar. Again, I'm writing out Y bar because it's hard to draw that arrow or the line over the Y. Okay, well, let's figure out AP. AP is this little area up here, which is just half this box. Well, we could sort of like do a similar cheater method by just getting the area of the whole thing and dividing it by 2. It might be harder to like actually look at this half one. Let's just get the big box minus the little box and then divide that by 2. We already have the values up here. So I'm going to do 8 inches times 10 inches. That's the same thing we got right here. That's the outer box, 8 inches times 10 inches. I'm going to subtract from 6 inches minus 8 inches. These are the same values I just used. I'm just not putting them into the area equation. That's the area of the entire thing. Big box minus little box. If I divide that by 2, that'll give me the area of the top right here, which is an easier process in my opinion, which gives us 16 inches squared. Boosh. Okay, so that's AP. Now the Y bar is the trickier one because we really need to look at this little guy. This little guy right here. Okay, let me scroll down a little bit and get in here. For space, let me make another text box off to the side right here. That would help. Okay. Now let's do the y squiggle for the legs. There's two of the legs that have the exact same dimensions, so just one of the legs is going to be what? Well, it's just going to be that 4 inches divided by 2. Remember, it's measured from this base right here, which is the center right here. So just 4 divided by 2 is 2 inches. Voila. Okay. Then what about the y squiggle for the top? So we know which one is up. I'm going to call this one like web, which I said leg earlier. And then this is the flange, the top part, like we did before, the top part up here. Now remember, it's still measured from the bottom. So that one is the 4 inches, which I'm getting from right here. 4 inches plus half of this thickness. The thickness, like I said, I didn't draw right here because it would be too tight, but you could see over here that it is 1 inch. So 4 inches plus 1 inch divided by 2. Oops, divided by. So that's 4.5. 4.5 inches is my y squiggle for the flange. Then now I was going to go down here and put that all into the y bar equation. So for overall y bar, that's equal in the numerator. It's there's 2 of these little webs or legs, if you want to call them. There's 2 of those. So I'm going to do 2 times the area. The area I didn't previously calculate, but we could see that it's 4 times the thickness of 1 inch. Right here, the thickness of these guys is 1 inch. So 4 inches times 1 inch gives me the area. It's y squiggle for those little guys we just did is 2. So 2 inches. So 2 times all of that because there's 2 of those guys. And then we're going to do plus the area of this top bar. We don't have a line where that's previously calculated, but you can just see it's 8 times its thickness from this graph is 1 inch. So 8 inch times 1 inch multiplied by its squiggle is 4.5 inches. All of this is the numerator, so all that needs to be divided by AP, which we just calculated, of 16 inches squared. And let me get some room here. And when I do that, I do all the math. And I get, for Q, 52 equals 52 inches to the third. Oh, this is for y bar, sorry. So 52 inches. I'm looking at the wrong one. Actually, my bad. This is 3.25. 52 is going to be our answer for Q. 3.25 inches for y bar. And that is 3.25 from the x-axis, or from this axis of interest up here. So it's 3.25. Then if I plug this into Q, to get Q is equal to the 16 inches squared times the 3.25 inches, which I just calculated. That gives me the 52 I mentioned earlier, and that's 52 inches to the third. Now I can plug this all into the tap max equation. Tau is equal to the VQ over I T. The V I give you in the problem statement up above, which is 250 pounds. The Q we just solved was 52 inches to the third. Oops, that's a second. All that is divided by the I, which we just previously calculated. Remember, it's the whole I, 410 plus 67 inches to the third. That's time the thickness. Okay, what thickness? Well, it's a thickness across this line. It's not a thickness across this line twice, it's just whatever that thickness is of either side because it's symmetrical. So it's just 1 inch. 1 inch is the thickness of the part that is crossing that line. So just 1 inch. Plug this into the calculator. We get a shear stress due to bending of 31.65 psi. There we go. That's how we solve this problem. Again, I'll reiterate that the trick is to consider the half of this for figuring out what Q is. And I drew myself a nice little picture to make it easier and to make it easier to explain to you guys as well. Okay, so that is the first example problem. I'll break these videos up into multiple example problems. So that's it for now.